Okay, welcome. This is Mr. Dahlstrom helping out with some studying tutor sessions. I wasn't able to record the Zoom meeting. I don't really like to do that if I have a student in class, so I had a student in class and we worked through some problems, but instead of working through them, I'm going to show some of them to you and kind of give you the kind of theory behind them, because there was a lot of for both of us, for both me and the student, there was a lot of conceptual understandings and all the epiphanies and everything starting to come together. So I'll try to show you the whole thing and then some other things we came across. Now, when we started, the person I was working with had already gotten past, so up to that point, this is as far as I'd gotten, and he had already gotten to 15. So we did the ones that are checked off here, so 17, 24, 29, 33, 34, 37, and 37. He did not look at the conceptual yet, but we can talk about a few ones conceptually. Let me just adjust some things here. Okay. So the blue means that everything was on the blue page, and the blue page is this one right here. So I have a tracking of when those are. So some of the things I want to talk about in the conceptual here. Let me open my book there. Try not to make this too long. Also, how you should view this is you should view this as a learning thing. This is not something that I don't make this so that you can just go to the part in the video, pause it, write down the answer, and just go on. If you're doing that, you can look up the answers any other place. This is to kind of explain some of the difficulties that I saw, or some of the kind of key connections here to bring this all together. So. Not all the conceptual. One of the ones that I was intrigued about was number 11. This is one that number 11, if you in the conceptual problems, is basically talking about you have a spring of a certain length, and if you take that same spring with the same spring constant, or sorry, not spring, you have a spring with a certain spring constant. If you then cut it in half, what happens to the spring constant? And honestly, at the very beginning, I was like, nothing happens. It's the same metal. It's the same thickness of that. But not understanding this, I have a really corny way of kind of thinking of this. I'm going to use my little stubby hands here. So if you can think of the coils in between the springs, the air in between the spaces here. If I have a long one and I compress it, there's more area to be compressed to cause that change in position, that x in our equation here. If you then cut it in half and you eliminate that, I have less area that can compress in order to get that same distance. That's kind of the conceptual way that I kind of came to that. And I did not know the answer. I said it was going to be the same, and I was like, why would the teacher assign something like this, and why would the book even ask this if it was something extremely obvious? And so I looked it up online, and I had my mind kind of blown. So you can actually see right there, number 11 means wow. Okay, so that was something that was interesting. I kind of related it to an analogy of density, mass, and volume, where if you have two objects, if you have an object with a greater density, so more filled. So I was thinking here. I know what you're saying. Okay, situation. If let's say that you have an object that is mostly kind of empty, but has the same mass as another object that is more filled. Okay, so there'd be different sizes. I was kind of imagining in my head like a loaf of bread that was very like airy. And then if you push that in, it's very easy to push in because there's more kind of air inside. There's more volume there. Then if you had something that was much thicker, there's less to compress, and so as you push them in, it requires more force to do that. It was a weird analogy, kind of just imagined in my head for that, and so that's something I will talk about. But I want to go over the problems because I don't want to be here all night. I ended at 4:30, and it's currently 4:50. So other ones that we'll talk about, we'll go ahead and look at number 17. Let me find where my number 17 is. Okay, number 17. So it would be ideal is to have your problems pulled up here, because this isn't going to make a lot of sense. I didn't necessarily write all this so that I could present it easily, so there may be some things that don't quite make a lot of sense, or some things written in the margins where maybe I and the student I was working with, we're talking about. So what number 17 is referring to? 17 is, probably help if I'm in the right unit. There we go. 17 is a black numbered one. If you don't know what a black numbered one means, in the book it means that's straightforward. The blue ones are intermediate, and the red ones are challenging. I think it's interesting. They say straightforward because they don't want to say easy. So sometimes when it's not always the best. When you look at the black numbered ones, as this one is here, you have to realize it should be a straightforward answer. So if you're overcomplicating it, you kind of need to step back and say, wait, this is straightforward. There should be some equation that I can solve for this. So what number 17 is, I'm going to put 17 up here. Keyboard out of the way. 17 says, when a 4 kilogram object is hung vertically on a certain light spring that obeys Hooke's law, that means it's F equals kx, the spring stretches 2.5 centimeters. If the 4 kilogram object is removed, how far will the spring stretch if a 1.5 kilogram? So basically, why they're giving you this information, notice that they're having to figure out how far something is stretching, but they're not giving you the spring constant. However, they're giving you enough information to find it. They're giving you the mass, which if you use gravity, can figure out the force of gravity. And they're giving you x, which you have to convert into meters here. So that's what we did. We realized here, go back to that if we use F equals kx, which is Hooke's law, and I'm ignoring direction this time because I'm just wanting the magnitude of this, that the force here is the mass times gravity divided by the distance here. So given the mass, we can calculate the spring constant. That's why they're saying in the second part of the problem, if you take off the 4 kilogram one and replace it with the 1.5 kilogram one, what is going to be the distance? So notice I rearranged this equation. Okay, so this one is now solving for x. I'm using the spring constant because it's the same spring constant we just found. The only thing that changed is the mass and therefore the force. And so we calculate this to be 0.0093 meters, which makes sense. Think about it. A 4 kilogram one is 0.025 meters or 2.5 centimeters. You put less mass on it, it's not going to stretch as far, so it makes sense it's only 0.93 centimeters. Okay. The second part here, 17, it says, where is it? Okay, here. How much work must an external agent do to stretch the same spring 4 centimeters from its unstretched position? So when I say external agent, that just means a way you can kind of imagine that is that you have the spring just basically tied in, like here it's not compressed, and then basically somebody is coming up to there, holding on to it, and they're stretching it so that it's now like that. There is some force being applied to stretch that a certain distance. So sorry, I'm going back and forth, need to do that. They say, how much work must an external force do? So when we hear work, we should be thinking about force times distance, okay? There's that thing. But another thing that really helps conceptually here is we have to understand that what work is. Work is how you put energy into a system. The system in this case is the spring. Or it's how you remove energy from a system, or necessarily removing it or reducing the energy as in the form of friction. So in this one, if we want to increase the energy in the spring, we need to do work in it. But realizing that we're pulling on it, okay? We're pulling on it in this case, so all of the work that's being done is being transferred into elastic potential energy. When we pull that down, it's going to have energy, potential energy, because I know that because if I let go of it, it's going to fly right back up. So in this case, the work is equal. It's really the change in elastic potential energy. But since there was no potential energy when it was at rest, we can simplify it to this. So it is 1/2 kx squared. We know k there, same spring. They ask us to move it 4 centimeters, so that's 0.04 meters. And we solve it, it's 1.25 joules. Now this over here, this is joules is Newton meters. Just realize that this can be confusing because joules is Newton times meter, where the spring constant is Newton over meter. Literally the unit exists so that when you take K times meter of X, you will cross that out and automatically get there. So that's a sort of placeholder unit. So that takes up, that's 1.25 joules. Another interesting thing of applying this is that, actually, we'll go ahead and leave it there. Just thinking another way to apply it, no way to get more complex. So that's 17, mark that off the list. The next one we looked at was number 24, which was a blue one. We see the blue one, not necessarily you have to get all anxious about that. Not a lot of room to show this book here. Okay. Like I said, you should probably have this in front of you. Okay, 24 is over here. It says a light spring with a force constant, spring constant of 3.85 newton meters is compressed 8 centimeters, as is held between a 0.25 kilogram block on the left and 0.5 kilogram block on the right. When I heard that there was 2 blocks being held to each other, I started thinking of the train and pulley problems that we did in pre-AP physics, and that you guys have done as well. But instead of a string, a rigid string in here that has tension, we have a spring here that that is compressed. We basically compress these two things. So there's elastic potential energy in there. So if we were to let it go, they would fly away. So the mass of the first one is 0.25 kilograms. The mass of the second one is 0.5 kilograms. The work that I set up for this one basically isn't as nice and neat for this. Let me try to... I was only solving the part that needed to be done here. Like I said, this is similar to ones we've done before where although there may be a force over here, the tension is the same. Now the reason that this tension doesn't cancel out is because they're not acting on the same mass. The same thing here. The force here that we figure out is the same on both blocks. Okay, they are not going to have the same acceleration. And this is Newton's third law to its core. They're going to have the same force, but they're not going to have the same acceleration because this mass is smaller and this mass is bigger. So I made it very akin to a rifle and a bullet. The force is the same, but the mass of the bullet is smaller, so it has a bigger acceleration, and the mass of the rifle is bigger, so it has a smaller acceleration. So back to this. They're asking us to figure out the acceleration on both blocks. Part A, which I didn't solve, it was already solved, is to figure out what is the acceleration when the coefficient of friction is 0. So if the coefficient of friction is 0, if we have our free body diagram for both of those, can draw both of them here. But I guess a way of looking at this, I guess I'll do it. I'm going to decide to define that as positive x and that as positive y for this one. That's how we solved it here. So we have the force of gravity, you have normal force, you have the tension in here, so you have a force pushing it this way, which would be the spring force. Force of the spring. And then you also would, because it's moving, actually these are kinetic energy, coefficient of kinetic friction. And then you have force of friction, kinetic back in the opposite direction. So defining it here to the right, so we have this way f of s minus f of k. Oh, that was one. That's just the equation here. This is the base equation. But for part A, I mean, you have no friction because the coefficient of friction is 0. So you just have the spring force equaling mass times acceleration. What is the spring force here? Let's see here. What we got here? The spring force is, we use F equals kx, and I'm using the magnitude here. So that's 3.85 times 0.08. So the force is 0.308 newtons. And so that is what our force is on both of those. So for part A, you would have just basically Fs1 minus m times a of x, and you can solve for the acceleration there. I don't have the numbers currently in front of me, but whatever 0.308 divided by 0.25, that's the acceleration for that one. And you say that's to the left. I'm using positive magnitudes to indicate this, so it would be moving to the left. For B, it would be very similar. You would have the same force. You would have no friction, but the mass for this one would be 0.5. So same thing for both of these. What 0.308 I'm sorry, that should be minus, that should be an equal sign. Sorry for all of you screaming at the screen. That should be 0.308 divided by 0.5, and that's the acceleration. And in this case, for the right block, it would be moving in the opposite direction to the right. Which is interesting to show here, because when you calculate those accelerations, although the force is the same, we were proving that the accelerations would be different. For part B, I do have this worked out. I'm sorry for the mess of I was basically not planning on showing any of this, so this is here. There. So for the second one, they're saying, okay, what is the coefficient of friction? Now the coefficient of friction for this one is 0.1. So you should be able to figure that out if you solve for what your normal force is, and then understanding that the force of friction is equal to mu Fn. You find out what your normal force is, multiply it times the 0.1, and in that case that comes out to be 0.245. There's our mass. We solve for the acceleration, we get 0.252 meters per second squared, indicating that it's going to the left. Similarly, we have to solve for the force of friction over here. It's not going to be the same as over here. Yes, the coefficient of friction is the same, but because the mass is more for the other one over here, it's going to have a bigger normal force, and then therefore a bigger force of friction. Okay, which makes sense. The force of friction is based on how much the two surfaces are pushing together. So if it's heavier, it has more friction. What we found in this case, if you look at this, is we have 0.308. So this is how much the force is, I guess in the free body diagram. I'm sorry if I didn't draw over here. It's basically the exact opposite. So 2, normal force, force of gravity, and the force of friction. And this one we're deciding that that is positive x. Just so we can get that. And so if we do that, we have Fs is 2 minus force of friction, which is this. But the force of the spring is less than the friction, and so if that's the kinetic friction, that means that this acceleration would come out as a negative, which means it's not even moving at all. This is not even possible for it to move. So if it can't overcome it. So that one is not moving. Okay, then the last part for C is now we're moving the coefficient of friction up to 0.462. So it's pretty easy for, I didn't answer this, but it's pretty easy for part C for this one because mass 2 is not moving. If it didn't move under 0.1 coefficient of friction over here, it's certainly not going to move with 0.462. And then we do over here with C, this is for the block on the left side, so mass 1, 0.308 minus the normal force, multiplied times 0.462, which is this. We can see that this number is bigger than that. And so in this case, we would get an acceleration that is not greater than 0, which means that this thing is not going to slide. It doesn't mean that it's going to be pulled back because friction doesn't pull on things, it just resists things. So that means it's also not moving. So in conclusion, I know those kind of everywhere. The force is the same, the accelerations will be different. When there's no acceleration, this one has a higher one than this one. Okay, we can calculate that one. For part B, when we have 0.1, this still accelerates, but this one can't overcome its own friction and does not move. And then for part C, with 0.462, this does not accelerate and this doesn't accelerate. Now, one thing I was talking about with the student I was working with, and I kind of had an epiphany here, and maybe I should have realized this earlier, is that let's just hypothetically say it was a different problem where this had a different coefficient of friction than this over here. The reason of drawing these blue lines here is saying these forces don't cancel out, and so the spring acting on that is acting on it the same as that. But the other thing to realize is that it doesn't matter the movement of this, whether this moves or whether this doesn't move. This is under a specific coefficient of friction. So let's say that's 0.1 and I don't know, that's 0.2. Okay, this doesn't have to accelerate. It could be still, it could fire back, it could do whatever. Under a certain specific coefficient of friction, if it's enough, or I guess a little enough to move, this will always move the same acceleration. Meaning that if you solve for a certain acceleration over here, and let's say that it was 3 meters per second squared this way, it doesn't matter whether you increase the coefficient of friction over here so this doesn't matter, or you decrease it so it does matter. This is still going to have the same acceleration because the acceleration is only based on this force right here. Okay, this thing moving away doesn't change the force over here. Doesn't change it in the very beginning. We're looking at the initial acceleration. Yes, eventually when they start moving away, they'll kind of pull back. But that was kind of an interesting idea, and I related it here to the rifle and the bullet. We just talked about this, where the bullet's acceleration is dependent on its mass. If I make the rifle much bigger, but I keep basically the explosion the same, the force the same, increasing the mass of the rifle will decrease the kickback, the acceleration, but it has no effect on this bullet because it's the same force acting on it, and that's why we say these are independent. That's why Newton's third law does not cancel out forces, because they're not acting on the same object. I thought that was pretty interesting. So that's 24. Let's see at my time. I might just, instead of creating long. There we go, 2 problems in 20 minutes. Okay. This isn't going. Okay, I'll end that. I'll post this, and when I'll have another video over the next 3 or 4. So we'll see that way.